Now let us consider one example by which we can find out the inverse, and we will be able to understand what is adjoint, what is cofactor matrix. So let us take the example as matrix A is equal to A, B, C and D. Let us take this 2 by 2 matrix. To find out the cofactor matrix for matrix A, I'll find out C11, that is nothing but the cofactor of A11 element. This will be equal to minus 1 to the power I plus j into, by removing this row and column, so we'll be getting D. So similarly C12 will be equal to minus 1 to the power 1 plus 2 C minus C. C21 will be equal to minus 1 to the power 2 plus 1, and by eliminating the row and the column corresponding to C, getting B, this will be minus B, and C22 will be equal to minus 1 to the power 2 plus 2 into A. This will be, so I can write the cofactor matrix as C is equal to C11, C12, C21 and C22. So if I substitute these values, I'll be getting D minus C minus B and A. And to find out the adjoint of matrix A, this is nothing but the transpose of cofactor matrix. So this will be D minus C minus B and A. I'm taking the transpose of this. So D minus C I'm writing as a column, minus B and A in the form of column. So now I got the adjoint of A. Now the next thing to find out the inverse is I need to calculate the determinant. So determinant of matrix is A into D minus B into C. So the A inverse is nothing but adjoint of matrix A divided by determinant of matrix A. So this will be 1 upon AD minus BC, that is the determinant, and the adjoint of this matrix is D minus B minus C and A. And each term can be divided by AD minus BC. So there are certain things, certain important things in order to find the matrix inverse. The first is determinant of A must be non-zero, then only we can find out the inverse of any matrix. And now let us take some short conclusion from the inverse of any matrix. And since it is a 2 by 2 matrix, so we can see the 4 elements A, B, C and D, and the inverse is nothing but the determinant and the multiplied by the adjoint. So what I can see in the matrix is here A into D, A and D elements are the diagonal, so these diagonal elements have been swept, and other elements B is coming with a negative sign and C is coming with a negative sign. So what I can say in short, that whenever we have any matrix, let us take another example and let's write down the inverse directly. So let us consider another example 2. So suppose I have matrix B, this is equal to 1, 2, 3 and 4. So if suppose I want to write the B inverse directly, what I can do is 1 divided by the determinant, so 1 into 4 minus 2 into 3, so 1 into 4 minus 2 into 3, and adjoint, so this will nothing but the diagonal elements can be swept, so this will be 4 and 1, and other elements can be written with a negative sign. So directly you can write down the inverse of 2 by 2 matrix. But for 3 by 3 matrix, you need to find out the cofactor matrix and we need to follow the procedure. Now let us talk about some of the properties of the matrix. So the first one is A plus B transpose will be equal to A transpose plus B transpose. You can write properties of matrix properties. So if I want to find out the transpose of this two, A plus B transpose will be equal to nothing but A transpose plus B transpose. The next property is A B transpose will be equal to B transpose into A transpose. Similarly, AB inverse is B inverse A inverse. Any matrix, if it is multiplied by the inverse of this, or otherwise inverse is multiplied with the matrix, then we will get the unit matrix I. If any matrix is multiplied by a scalar k, and if I am taking the transpose of this, then this will be equal to nothing but k times of A transpose. K can be taken out, where k is a scalar and A is matrix. Similarly, Ka inverse can be written as K inverse A inverse. The A transpose, and if I after that if I take the complex conjugate, it will nothing but the same, taking the complex conjugate and then taking the transpose of the matrix. Now the another property is related with adjoint. So adjoint of A, the determinant of adjoint of A is nothing but the determinant of A to the power n minus 1, where n is the order of the matrix. And if I want to find out the determinants of adjoint of A, this will be equal to determinant of A to the power n minus 1 whole square. Now let us talk about the elementary transformation of matrix. Elementary transformation of matrix is important operation which we need to apply to find out the rank of the matrix, to find out the inverse of the matrix. So the property, the first elementary operation what we can apply is the interchange of the row. So let us take example, and with that example we'll try to understand. Let us consider this matrix 1 2 3 4 5 6 7 8 9. This is matrix A. So the first elementary transformation says that the interchange of any two rows it means I can apply the elementary row operation as R1 interchange to R2 in the given matrix. Then I will get 4 5 6 1 2 3 and 7 8 9. So this operation I can apply in the matrix. I can interchange any of the two rows. The second elementary transformation is the multiplication of a row, multiplication of a row by a constant, generally denoted by k r1, let's say. So I can multiply any scalar to any of the row. So if I multiply this k constant, it can be any number 1 or 2 based upon the operation which we want to apply. So if I multiply k to first row, then I will be getting 4k, 5k, and 6k. 1 2 3 7 8 9. This operation I can apply. And the third operation is the addition of constant multiplication of any row to another line. So in mathematical format we can understand it better. Let's say I want to make this element to be 0. So in order to make this element to be 0, I can do the operation R2 tends to R2 minus 4R1. So any row can be multiplied by any constant, and it can be added or subtracted from any row. This operation I can apply as an elementary transformation in the matrix. So if I do this operation with the initial matrix A, as you can see here, then I'll be getting 1, 2, 3. Then 4 minus 4 is 0. 5 minus 2 into 4, 6 minus 3 into 4, 7, 8, 9. So this will be equal to 1, 2, 3, 0. 5 minus 8 is minus 3. 6 minus 12 is minus 6. 7, 8, and 9. So this kind of operation we can apply as elementary transformation of the matrix. And the important thing, elementary transformation doesn't change the rank of the matrix. Does not change the rank of the matrix. We'll talk about the rank in the subsequent topics. However, it changes the eigenvalue. However, it changes the eigenvalue of matrix. So this elementary transformation we understood, because the next topic what we are moving towards is Gauss-Jordan method to finding the inverse. There we will apply a lot of elementary transformation, and we should have sufficient practice in elementary transformation in order to avoid the mistakes. And the second place where we are going to use this elementary transformation in finding the rank of the matrix. So let us move to the next topic, which is the Gauss-Jordan method of finding the inverse. So the next is the Gauss-Jordan method of finding the inverse. So what this method says, let us take one matrix A, which is nothing but minus 1, 1, 2, 3, minus 1, 1, minus 1, 3, and 4. If I want to find out the inverse of this matrix, I can apply the elementary transformation and I can convert this matrix into a unit matrix. And at the same time, if I apply this operation to a unit matrix, then whatever the results will come, that will show the inverse of the matrix. Let's understand it in a better way. So let us write it in this way. Again, I am writing the same matrix: minus 1, 1, 2, 3, minus 1, 1, minus 1, 3, and 4. This is my matrix A, and on the right hand side I am writing a unit matrix: 1, 0, 0, 0, 1, 0, and 0, 0, 1. Now what I need to do in order to find out the inverse of this matrix is, on the left hand side matrix, which is the matrix A, I will apply elementary transformation and will convert the left hand side into a unit matrix similar to this, which is looking on the right hand side. And whatever operation I will apply on the left hand side, the same operation I will apply on the right hand side. And at the end, when this matrix, left hand side matrix, will be converted into the unit matrix, I will see what matrix I have on the right hand side that will show the inverse of the matrix. So let us start. So if, as a first operation, if I apply R2, I am applying the first operation in R2, which is nothing but R2 plus 3R1, in order to make this as 0. And the same time I can apply R3 operation in R3, so R3 minus R1. So if I apply this elementary operation here, I will be getting minus 1, 1, 2. There is no change in the first row. In the second row, I am making R2 plus 3R1. So I am multiplying by 3 to the first row and adding to the second row. So I'll be getting 0, 2, 7. Similarly, I am subtracting from row 3 to row 1. So I am getting 0, 2, 2. And on the right hand side, if I apply the same operation, I will be getting 3, 1, 0, minus 1, 0 and 1. Now I got two zeros here. Now the next thing is I need to make 1 0 here. So at least it will be converted into the upper triangular, and then I need to take care of the other part, this 3 elements also, to make it to 0. So the next operation what I can apply here is R3 in the row 3. So row 3 minus row 2. So if I apply this operation here, I will be getting minus 1, 1 and 2. 0 to 7, because there is no change in first and second row. I'm simply subtracting from row 3 to row 2. So this will be 0 minus 5. The same operation, 1 0 0, 3 1 0, and this will be minus 1 minus 1 minus 1 minus 3. This will give me minus 4 minus 1 1. So now I have all the three zeros here. I need to make three zeros here also. So again, I will be applying the row operation. R1, I'm multiplying by a scalar minus 1 to make it positive, because in the unit matrix I need a positive here. Then the second thing, R2 is nothing but R2 divided by 2. Then I'll be getting 1 here. The third is R3 is minus R3 by 5 in order to make this as 1. So this will become 1 minus 2, multiplying minus 1 by first row. Similarly, if I divide by 2 to the second row, 0, 1 and 7 by 2, and this will become 0, 0 and 1. On the right hand side, I can see minus 1, 0, 0. This will become 3 by 2, 1 by 2, 0, and this will become 4 by 5, 1 by 5, and minus 1 by 5. So the next operation I will apply to make this elements to be 0. So what operation I can perform here is, in the row 2 is equal to row 2 minus 7 by 2 times of row 3, because this is 1, this 1 I can use in order to make this 0, and it will not be affecting this elements. Similarly, R1 is nothing but R1 plus 2R3. So if I multiply by 2 and add to this, then it will become 0. So this operation will give me 1 minus 1, 0, 0, 1, 0 and 0, 0, 1. And similarly, if I apply the operation on the right hand side, we can do this calculation. This is 3 by 5, 2 by 5, minus 2 by 5, minus 13 by 10, minus 1 by 5, 7 by 10, 4 by 5, 1 by 5, minus 1. So the last thing I need to do is to make this minus 1 to 0. So I can simply add R1 and R2. So I will get 1, 0, 0, 0, 1, 0 and 0, 0, 1. So on the right hand side, I will get minus 7 by 10, 1 by 5, 3 by 10, minus 13 by 10, minus 1 by 5, 7 by 10, 4 by 5, 1 by 5, minus 1 by 5. So the original matrix A is converted into the unit matrix form, and unit matrix has taken the another form. So the A inverse, this matrix will show me the inverse of the original matrix A. So in this way, we can find out the inverse of any matrix by applying the elementary transformation. The next topic is rank of the matrix. A matrix is said to be of rank R when the first is it has at least one non-zero minor of order R, and every minors of higher order higher than R should vanish. What it means, we will just understand with the help of one example. Let us consider this example of 3 by 3 matrix 1 1 1 2 2 2 and 3 3 3. Let us take this matrix A, and suppose I need to find out the rank of this matrix. So as per the definition what we have written over here, it says that the rank of any matrix is said to be R when the first is it has at least one non-zero minor of order R. The concept of minor which we talked earlier, as we have seen in case when we are talking about the minor. So if I am taking any matrix of order 3 by 3, then it will have one minor of order 3, means the determinant of the matrix itself, that is the minor of order 3. Then it will have the 9 minors of order 2 by eliminating the rows and the column corresponding to each element. I can get 9 minors of order 2, and similarly each element by removing the two corresponding rows and columns, I can get the 9 minors of order 1. So what I need to check in this matrix is I will always start with the highest order minor. So in this case, since the rank is 3, so there is only one minor of order 3. It means I will check the determinant of this matrix 1 1 1 2 2 2 3 3 3. And as we know, so if I calculate the determinant of this matrix, it will become 0. So when this is becoming 0, then I need to check for the order 2 minor, and as we have seen here, there will be total 9 minors of order 2. So if one of them will be non-zero, then I'll call the rank of the matrix as 2, and all the minors of order 2 will be 0. In that case, I need to proceed for 1. So let us understand it in a better way. Again, let's go back to the definition. So it has at least one non-zero minor of order R. Since there was only one minor of order 3 and that is 0, so the rank cannot be 3. So here I can write rank cannot be 3. Now, in order to proceed for 2 by 2 order minor, I can I can write I can start writing from A11. If I remove the rows and columns, so I'll be getting 2 2 3 3. For A12 I can write 2 2 3 3, and similarly all the minus I can get. And if you calculate all the minus, then in this case all the minus of order 2 will become 0. Then in order to see the first order minor, since all the elements, at least one of the elements, if it will be non-zero, then the rank will be 1. So here, since 2 by 2 order minor, all the minors are 0, so I can write rank cannot be equal to 2, and Since all elements are non-zero, so I can write rank is equal to 1. In this case, all the elements are non-zero, but I need at least one element should be non-zero. Then also the rank will be equal to 1. So with this example, we can see the rank of the given matrix will be equal to 1. We can take another example: 1 2 3 2 4 6 3 7 8 8. So in this case, if I calculate the determinant of this matrix, so I'm directly writing the determinant. So determinant of A is nothing but 1 into 4 into 8 minus 2 times of 2 into 8 minus 6 into 3 plus 3 times of 2 into 7 minus 4 into 3. So I'll be getting 32 minus 2 times of 16 minus 18 minus 2 is 3 times of 14 minus 12, that is plus 2. So this will be 32 plus 4 plus 6. So I can say that is not equal to 0. In this case, 4 into 8 minus 6 into 7. So it will be 32 minus 42. So it will be minus 10 here. So this minus 10 and plus 10 will become 0. So the determinant of A will be equal to 0. So since the determinant of this matrix is 0, it means the third order minor is 0. So the rank of this matrix cannot be equal to 3. Now I can check for all the minors of order 2, all the 9 minors of order 2, and if one of the minors will be non-zero, then in that case I can say the rank of the matrix is 2, and we can follow the similar procedure as we have done for the previous example. But it is a laborious way to find out the rank of the matrix. So we have a systematic way by which we can find out the rank of any matrix, rank of any matrix of higher order than 3. Let's say for example 4 by 4 matrix. So in that case it will be difficult to find out the rank in this way. So we will talk about that method. One more conclusion we can draw by seeing this example: the rank of another definition of the matrix, the other definition of the rank can be written as, and this definition will help us to understand the rank of the matrix. So in the first example, let me write down the definition first. So the definition goes like: rank is nothing but the number of linearly independent row vectors. So in the first example, we can see 1 1 1, 2 2 2, and 3 3 3. So the second and third rows are nothing but the dependent rows, which can be obtained by multiplying 2 and 3 to the first row. So there was only one independent row in the first example. So the rank of the matrix was 1, as we have seen already. And in this case, if we see 1 2 3 and 2 4 6, so the second row again it can be obtained by multiplying 2 to the first row, but the last row is not a dependent row. So in this case the total number of independent rows are 2. That's how the rank of the matrix is 2 here. Now one another special case special case for rank of square matrix. So the rank of the square matrix is nothing but number of non-zero rows in upper triangular matrix. Means any matrix we will convert into upper triangular matrix, and we will see how many number of non-zero rows are there, and this upper triangular matrix conversion we will do using elementary transformation, which we have talked just now.